Okay. So let me share. Okay. So as I mentioned that today we have discussed about three different coordinate systems. And now I think I'll discuss that how to transform uh, one coordinate system to another coordinate system. It is essential because the horizontal system, which is quite often used because it is very simple and quite obvious. But I think that is observer dependent, his position, time, etc. So therefore, it is essential to convert these to another coordinate system which is independent of the observer and other things, which are the permanent features of the objects which are being considered. So I think that we will discuss, and I will pick up only in details. I will discuss the transformation of horizontal system to equatorial system. Then to ecliptic, etc. Also, I have the slides. I'll just share it, and anybody who is interested can do it later. But it is not to be done now. But before I discuss that, there are two, three things I would like to mention. First of all, this one. So you can see what I have shown that this is the celestial sphere, and this is the globe of the earth. Now, if somebody is standing here, his horizon will be this plane. That will be his horizon, tangent to this. This will be the zenith, and so on. And he will see objects rising here, stars, etc., and they're setting here. Now the question is that it like this, that means this horizon plane, is it dividing the celestial sphere into two equal parts or two unequal parts like this? Actually, the globe of the earth is so small compared to the size of the celestial sphere that if you shrink it, it becomes a point. And the configuration becomes this. This becomes the horizon plane, and this is the horizon circle. Now, this is a case because the celestial sphere, its size is much, much, much larger than the globe. So it becomes a point. And therefore, you can see the horizon plane is dividing the celestial sphere into two equal parts. Now, ancient astronomers recognized this fact that Earth is too small compared to the celestial sphere. What they did, they noted the rising of some stars which are located on the celestial equator. And at the same time, they saw that what is rising here and simultaneously what is setting, which star. So after 12 hours, they expected that this star will rise and this star will set. Now, that is possible only if the celestial sphere is divided into two equal parts. That means the Earth's globe is too small, it becomes a point like. That they found even in ancient time that the celestial sphere is divided by the horizon plane into two equal halves because Earth is extremely small in size compared to the celestial sphere. Actually, celestial sphere has no size because it is not a sphere, it is just empty space. So now I think another point which I have to discuss, I didn't mention in the previous class when we are discussing horizon system. Anyhow, now you see this is the horizontal plane. This is the north point. So this is the north-south line for the observer. This is the observer standing. And so this is the zenith, vertically up. Now, and this is the pole, celestial pole. That means this is the axis about which Earth is rotating from this side to this side. Relatively, sky or heaven is rotating in the opposite direction. So therefore, say, for example, sun. Now, one thing I think what we have to keep in mind, this meridian circle, it's a great circle, which is passing through the north point, the celestial pole, and the zenith point. This is called the observer's time meridian. or prime hour circle. Now, the stars, etc., what is considered that when they are crossing this is called transit. So, how much it has rotated after crossing the vertical, this prime hour circle of the observer, that means suppose this it was here in a plane, this whole thing is this plane containing this object is rotating about the Earth's axis. So this angle is the amount of rotation of the object. It can be anything. That is called the hour angle. That means from the vertically top position when it was on the prime meridian, it is considered positive if it is towards the west, and it is considered negative if it is towards the east. Our angle, is sometimes it is given in time also, because 15-degree rotation is equivalent to 1 hour, that we know. So both are there, but angle is perfectly all right. So this is very important, because when an observer sees an object like this, so he has to also find out its location. And this is important because it is dependent on the time. So this is called the hour angle, which will be very important in discussion when we will just now will have for transformation. So this was not discussed earlier, the hour angle concept. And this hour angle depends on the observer's position on the Earth's globe, where he is located. So a particular star, its hour angle, that means his prime meridian will be different. Every observer has his own prime meridian. And so when a star crosses that, the transit, that point will be different for different observers. That's why this is important when you want to convert the observed position into a system which is independent of the observer. Now, this, I think I'll use pen and paper just now, but before that, I'll show what we are going to do. So this is the celestial sphere, and this is the horizon circle, the green one, and this is the observer. This is the north point, this is the south point, this is the north-south line, and this is the vertically up direction, zenith. And this red circle passing through N, Z, and S is the observer's prime meridian, and which also has the uh, pole star. Now, so a particular object, so this is the prime and this is the horizon circle. Now, suppose this is a star you want to identify, you know that this great circle passing through the zenith and the star, it's the horizon circle here. We call this point A. Now, you know that this angle is the azimuth and this angle is the altitude. They are written as capital A and small a. Now, what we have to do now, so this we already know. Now, what we have to do, we have to convert these two coordinates into an equatorial system. Which is the equator? The celestial equator is this one. This is the pole star. So this is the axis of rotation. So this is the celestial equator. So here you will find that you have to convert. There, how do we? There is a reference point from where we measure the right ascension and declination. So what will be the right ascension of this one? It will be this point. So from the reference point, say this one, from this reference point, whatever reference point I choose, this is the right ascension, an angle or hour, and this angle is the declination. So we have to convert them. So that's what I think our task, and we will do that. Now, same thing we have shown here. The equatorial system is shown in red. This is celestial equator. So this is the reference point, whatever reference point for which we measure the equator. It could be the Greenwich meridian point. So this is the right ascension called as alpha, and this is the declination delta x. and that is the equatorial system. And the horizontal system, this is the azimuth, and this is the altitude. Our job is that given the observer's latitude, now which is the latitude of the observer? Obviously, this is the latitude of the observer. The inclination of the pole star direction. Okay? And azimuth is given of the object, altitude is given. These are the three things given. You have to find out the right ascension on alpha x and declination delta x of the same object. That is our task. So now you see, if you draw the great circle through this object and the z, you get this great circle. This is the another great circle, which is the prime meridian of the observer. And this is another great circle which you are drawing for the purpose of the equatorial system. So this becomes a spherical triangle like this. And in this spherical angle, the sides, three sides are what? This side will be what? This is 90 degree. 90 degree minus a. Zx is that. How much will be that? 90 degree minus 5. And how much will be this? It is 90 degree minus delta x. So we'll consider this spherical triangle and do our conversion. Let us do. So you have that formula. If you remember that if there is say if you call A, B, C, this is A, B, C, and this angle is capital A, then you know we have derived it that cosine A is equal to cosine B into cosine C plus sine B into sine C into sine K. This is the formula, fundamental formula. We use nothing else. Now this we can do it for this as A, or we can do this as A and this as the capital A. Both all, but formula will be same. So now I think using this formula, first I think what we have to do for conversion purpose. So let us consider this. Say cosine of Px is the object. Cosine of Px will be equal to cosine of Pz into cosine of Zx plus sine Pz into sine Zx into sine of, now this is the Px you are taking, so this is what angle? This is important. This angle you can see is nothing but the amount of, that means if you draw a tangent to the west, so this goes to the north.
But the tangent is not visible.
No, tangent you have not drawn. I'm saying that tangent towards north is this. How much it has to rotate to come to this tangent? It is nothing but the azimuth. Okay. So this angle is nothing but the azimuth, sorry, 2 pi minus a. Is it okay? This is 2 pi, 360 degree, and you are subtracting the azimuth a angle, so you get this angle. So this angle is equal to 2 pi minus a. So that's what you're looking here. Now, how much is cosine Px? Px is 90 degree minus delta x. So cosine 90 degree minus delta x is equal to, now Pz is equal to 90 degree minus 5. It will be sine phi. Cosine 90 degree minus phi means sine phi. You know that. Basic trigonometry class. Cosine zx, how much is this? It is 90 degree minus altitude. So it is sine A. Plus, this becomes just opposite, it becomes cosine phi into cosine A into cosine A. Cosine 2 pi minus A is cosine. That all we know from the basic trigonometry. So therefore it becomes sine delta A. So therefore what we can get? We get delta x from this equation. Sine delta x is equal to this. So when A is given, altitude is given, latitude is given, so right hand side is completely known. So if this is known or given or can be calculated, that gives you delta x, which is equal to sine inverse. So therefore you get delta x. Next what we do? Next what we do is we take this one, take cosine zs. What will be that then? If the cosine zx in spherical trigonometry, if you use the same relation, it will be cosine of this into cosine of this plus sine of this into sine of this into cosine of this angle will come. So therefore it will be cosine of pz into cosine of px plus sine of pz into sine of px into cosine of this angle. How much is this angle? This angle. How much is this angle? You can see this angle is nothing but the angle rotated from this great circle to this great circle, isn't it? This great circle to this. So it has rotated this much. This angle is that, this tangent and this tangent, their angle is this. And this is what? This is nothing but the hour angle. That's what I discussed. That means the amount of rotation towards west from the meridian, the prime meridian. So this is the prime meridian. It is rotating about this axis. So the amount of rotation is, this is what is called the hour angle. So therefore this becomes cosine zx is what? Zx is 90 degree minus A. So it will be sine A is equal to cosine pz will be sine phi. Cosine px is equal to sine delta x plus cosine phi into cosine delta x into cosine h. So now you see what we get from this equation. From this equation, we get cosine h. Cosine h, you can be written as sine a minus this minus sine phi into sine delta x divided by cosine phi into cosine delta x. Now delta x already you have found out from the previous equation, so you can substitute here and you get cosine h. You can get sine inverse. Now, once you get the h, how to find out the right ascension of this? As I mentioned, that what is the right ascension of the observer? This is the right ascension of the observer from the reference point along the equator, celestial. And what is the right ascension of the object? Is this one. So alpha x is nothing but what? Right ascension of the observer minus our angle. So this gives you or the right assumption of the, this is nothing but right assumption of the x. So therefore, we have found out alpha x and we have found out. That's how you can transform your coordinates found out from your observation in a horizontal coordinate system to an equatorial system, which is, of course, a standard system. And of course, from this, again, from equatorial system, you can again convert to ecliptic system. Now, I will not go into the detailed math of that. So this is the diagram, and I have done it with hand because I felt it will be easier to follow. Now, is there any question here? Because whatever we will do with the help of this one. Is there any question on this part?
If anyone has any question, they can unmute themselves and ask
Yeah.
the question.
Yeah. Any confusion you can clear.
So one small question, like,
Yeah, please.
so with regard to this a spherical triangle, like BAC that you have highlighted. Now, will the same and the by which the formula was actually used, and we can find out certain things. But my question is whether this formula is applicable for any other type of spherical triangles.
Yeah, spherical triangle, because the formula which you have derived, you can see that there is, say, for example, how we did it. This is a good question. How we derived was, we considered that while deriving the formula, we considered that this is the sphere, any sphere, and here this is the center of the sphere, and we considered a spherical triangle like this, where this is the point where the plane is touching, and we drew triangles like this. Remember, this was the diagram we used. Now, actually, this is a, if you can call the A, this you call say B, this is C. Now, suppose any substrate, you can always consider, suppose you want to say that this point you want to make this, you can always do that, because this is again, so therefore, actually, this is a perfectly general case, though we used it for derivation of that. So we have used it for solving that distance problem, which I told Gustav to give, say, this is one great circle, this is another great circle, and this is another great circle. This is the North Pole. You remember that position A and position B, we found out the distance. Apply this. So, though it may look, it's a very special case where this point is touching a plane, you can do it for any triangle you do. I can take this point as the touching point.
Right.
And the same formula will come.
Okay.
Now, I think, as you can see here.
But one another small, point. So, from the mathematical perspective, this looks okay to me. But if we look into the Earth per se, there can be so-called mountains. There can be even gorges.
No, those are the deviation from the perfect case. The theory, what we have, trigonometry has done with a pure geometric case.
Okay, got it.
Mountain, etc. will now. So therefore, now you can see here that here what we did, this length was A, this length was B, this side was C, and the angles were like this angle is B angle, this angle is A angle, this angle is capital C angle. Now we derive this, that cosine A is equal to cosine B into cosine C plus sine B. Just now we used it also, sine C into cosine capital A. Now if you do it for side B, then you can write cosine B
Okay.
is equal to cosine A into cosine C plus sine A into sine C into cosine capital B. If
Okay.
you do it for this C, then it will be cosine C equal to cosine A into cosine B plus sine A into sine B into cosine C. So they are basically the same formula. Considering, so which one to use depends on what you want to find. Like say for distance between LA and New York, we consider this is the thing we have to find out. This was known, which was nothing but the co-latitude of LA. This is again nothing but the co-latitude of if you remember. This is the latitude of LA. This is the latitude of New York. So this is nothing but the co-latitude of LA, and co-latitude means 90 degree minus x. This is co-latitude of New York. So these things known, and what is this angle? Angle between these two, which is again nothing but the difference of their longitudes. So therefore, this was known, this is known, this is known. So you can. That is the way the spherical trigonometry is used.
So that clear, sir, clear.
So I think, so therefore this horizontal system to equatorial system, we have discussed in great details, and this is what I think, same thing what we have done, that is explained here. But I think, I hope my explanation was perfectly all right, but this you can keep for future reference. So this is what we have done. You can see this is the horizon circle, and this is the celestial equator. So there is some point which is the reference point, say from where we measure the distance, angular distance, we call it right ascension. In place of longitude, in case of Earth, we call it longitude. And the height above the celestial equator, we call it the declination. So this is nothing but the 90 minus declination. This is the zenith angle they call, which is again nothing but 90 degree minus the altitude angle. And this is again the latitude angle. So this is again nothing but 90 degree minus. So again, this is the spherical triangle which we have used and applied the formula straightforward. Here this A is shown wrongly. It should have been this way. It has to be always measured clockwise when viewed from the top by convention. So it is slightly mistaken. So, but I think you should correct it. I don't know. I couldn't correct it because it is already printed. So that is what we have done. Now, these are the same thing, just what we have done. Those things which are, you can see cosine A with this. So this is what actually when you have given in the equatorial system where delta and our angle, they are given, then how to find out the coordinates in the horizontal system. That is used when you want to set up your telescope to observe a particular star whose latitude, longitude, or whose right ascension and declination, they are known. So then you have to, if you are observing, so you would like to see what will be their position in the horizontal system. Then you do the reverse transformation. Reverse transformation will be also quite straightforward. You can see that equatorial to horizontal, if you want to say. So how do you do it? So it is just the reverse. What you consider that if you take that diagram, this diagram, so this is X, this is P, this is Z. So you have been given delta and right assumption. And you have to find out that you are setting up your telescope and in which direction you should observe. So then you need the conversion from equatorial to equatorial to equatorial to horizontal system. Then you need it. But it will be again perfectly all right using the same kind of uh, system which has been given. Now, how I will show it that also in little details. So now this is our celestial equator, this is zenith point, this is the north point, south point, head, this is the observer, this is the pole star. Now the object is and this is the say celestial equator, perpendicular to this. Say this is the reference, and object in this you have been given its position here. So therefore, in equatorial system, this will be given and this will be given. This is the right ascension alpha and this is the declination delta. What you have to find out? That we have to find out the coordinates in the horizontal system that you can set up your telescope. So what are those? Those are, that means this is a great circle, comes up to this. So you have to find out the azimuth and altitude. You have to find out. So again, you consider triangle, spherical triangle, PZX. So now what are the given things? Alpha x is given and delta x is given. Now you can see that this is the hour angle and the right assumption of the observer is nothing but alpha x plus. Now this hour angle is something, how do you find out? Suppose when you fix up your time, how do you do it? You know, our whole time, etc., is connected to sun. And what we see that Greenwich is the meridian whose local time is the standard time of the whole world, and we change it according to our longitude. We all know that. But astronomers are not interested in only sun's rising and setting. They are concerned about the whole universe. What therefore they use a particular thing which is called sidereal local time. What is sidereal local time? Now there, time is measured from the instant when a particular star or object which you are considering, it crosses the prime meridian. So that is considered. So therefore, they consider the reference point is that when that say reference point is your vernal equinox. When vernal equinoctial point crosses your uh, prime meridian, that is the point from which you will measure the time. So if it is say say for example the reference point, when this reference point, so you know this time that when it has crossed and how much it has gone, and the hour angle of this object will be then therefore this much, and so you can find out this angle. Okay, and why this angle will be important, that you have seen before. Now we have to apply the reverse formula. Reverse formula will be what? A sine of, sorry, I should start from, say, let us consider px. So cosine px is equal to cosine, we start from this or different one. Let me check. I think we have to start from another. So Pzx, we have to consider this one, Zx. So cosine Zx equal to cosine Pz cosine Px plus cosine Pz into sine Px into cosine. If this is there, then this angle. Now, what is this angle? This is nothing but the hour angle, which is known. Because if you have been given this, and this much is also known, it is the observer's position. So therefore, difference between the two is the hour angle. So this is known. So actually, what will be given here is that will be given as alpha x, not directly, to h and delta x. Now, how much is cosine zx? It is nothing but, this is altitude. So it is 90 degree minus altitude. So it is actually sine A. Sine A is equal to cosine Pz, which is sine of phi is sine of delta x plus cos of phi cos of delta x sine h. Now this equation, delta x has been given, h has been given, so therefore you can find out A. So altitude you have been able to find. That is in the horizontal coordinates. Now to find out the azimuth. How do you find out the azimuth? Azimuth you will find, if you consider the which side of the, that we have to find out this angle. So you have to consider this. Cosine px will be equal to cosine pz into cosine zx plus sine pz into sine zx into cosine of, this angle is pi by 2 pi by minus azimuth, or it's cosine px is equal to sine delta x is equal to sine pz is sine phi, this is 90 degree minus phi, cosine zx is sine A plus cosine phi cosine A into cosine. So here this has been given. This you have already found out from here. This has been given and this is known. So therefore what you can find out from here? You can actually, sorry, you can find out cosine. So cosine A is equal to sine delta x minus sine phi into sine A by cosine phi into cosine A. Delta x has been given, I is known, A you have already found out from the previous equation. So this gives you the azimuth. So that's how you can convert the data from equatorial to horizontal, which you need sometimes need to set up your telescope. That will be in horizontal system in many cases. So then you can do that. I think Subroto will quite often perhaps may need this. So this is what I think basically. Now I think if you want to go to equatorial ecliptic system, I will not go into the details. They are here. These are the, you can see this hour angle, RAX, these things are all explained. So this is how the hour angle, that is the previous one, that means converting from horizontal to. So this is the thing what we have been doing so far. This is in a better way. This is the pole, this is the latitude, so this is the pole latitude, this is the zenith, this is the hour circle of the object, this is the longitude circle of the object in equatorial system. This is the object. So the same thing what we have been done, that this diagram is little bit more detailed. So these are the equations what we have been doing. So you can go through these things. So it is the same derivations which we are doing. Same thing given in a condensed form. So here are to practice. So I have given a problem. Prove that the celestial equator cuts the horizon at azimuth 90 degrees and 270 degrees at any latitude except the north and south poles. At what angle does the celestial equator cut the horizon? At latitude pi. Please solve these two problems, or this problem. I think it is a good exercise, just to give you a little better grip on the things you have been discussing. Now, this I will not discuss this in details. I have been given. This is the ecliptic system, where I mentioned that this is the ecliptic and this is the celestial equator. Now, if you have it in the celestial equator, that coordinate system, you can convert it into ecliptic system. Here, this vernal equinoctial point, because of the Western or standard system, we use a cyano-longitude. So it starts from the vernal equinox point, the object's longitude circle, and that is the latitude. So now this shows the coordinates from equatorial to ecliptic. So this is the reference point where vernal equinox. So equator is this point. If you find out the alpha, which is given, which is equivalent to right ascension with this as the reference point, and this is the declination. These are the two things which will be given to you. This angle is the obliquity, 23.5 degrees, you know that. This is the object. So this is the longitude or latitude, delta, and this is the longitude will be this one. So there you have to measure this longitude along this, from this vernal equinoctial point, because it is the cyano system. And so therefore, now if you consider this spherical triangle, again you can do the same kind of exercise. Those of you who are interested, you can do it. I've given it here, but I think you can take it as an exercise. Only thing, how much is this length? This length is, now remember, this Z is different Z, I'm sorry. So this is P, this is Z, and this is X. So this side is nothing but 90 degree minus the right latitude, beta, in ecliptic system. How much is this? This is 90 degree minus delta, declination. So this angle, this is known. And this is again nothing but the co-latitude, that is 90° minus phi. So I think again using the same kind of formula, you can convert from one to another. So the result is this. That means the longitude will be lambda given by this in ecliptic system. These delta and alpha are the coordinates given in the equatorial system. So you can get lambda, and beta will be longitude will be this, latitude will be this. Now I think only one other thing I will discuss here is the rising and setting. It is interesting. Suppose you have seen that the position where sun rises, it changes every day depending on the time of the year and etc. So our objective here is to find out at which particular azimuth on the horizon circle the sun or any star rises particular day. How to find it out? So this is very interesting, and you will see that using this spherical trigonometric, you can easily do it, and the formula is quite simple. So that way, suppose for example, if Subrata wants to find out that he goes early morning and wants to see the sun when it is rising, he has to focus his telescope towards the point where it is going to rise. How he will know it beforehand? So that's what I will discuss now. Now again, I have drawn the celestial sphere. This is the observer, and this is the north point. This is the pole. The whole heaven is rotating like this about this axis, and this angle, of course, is pi latitude of the observer. Now, say for example, any object here, how it is moving. Now, since all the heaven is rotating about this axis like this, so this will also move in a circle like this, which we call as the latitude circle. This is the equator, celestial equator. So all these circles are parallel to this, but they are definitely different in size. And this is a horizon circle for the object. So if an object is here, so its latitude circle will be a circle passing through this and touching the celestial sphere. So as you go more and more towards north, its size becomes smaller and smaller. They are not great circles. Now the question is that this object, it is going through this. What we mean by rising? We mean by rising that this is the horizon plane. Whenever it comes above this horizon, that is rising, we call it. And when it goes just below this, that is called this. You have to find out what is the azimuth of the rising point. Now, symmetrically, you can say the azimuth of the setting point will be 2 pi minus. You can easily see. Now, you have to find out this azimuth. So, what you have to find out? Azimuth of x at rise. Now, what do you mean by azimuth at rise? Rising means what? What is a special condition in the horizontal system when you consider something is rising? What do you mean? Now, what we mean by rising is that this object's altitude is how much? Subrata, can you tell me what will be the altitude of rise? How much? What is the definition of altitude? It is the inclination of the object from the horizon, isn't it? So if it is at the horizon, on the horizontal plane, what is its altitude? 0. Similarly, setting also it is 0. Now, you know the formula we have just derived for the altitude. What is the formula we have derived? That sine of A is equal to sine of phi in, just now we derived sine of declination plus cos phi into cos declination into cosine h. But that is, this h is given in the horizontal, your ecliptic system. So we have to consider the relation for the horizon system. So that is what sine delta, we derived another relation, sine delta equal to sine phi into sine A plus cos phi into cos A into cos. This is the formula we need, which we derived. Now here, at rise, A is 0. So what will be the, and declination is what? That means what you can say, you have to find out A. So you can say cosine A is equal to sine delta minus sine phi into sine A by cosine phi into cosine A. Now this you have to find out how much is A. What are the given things? The object's declination is known, your observer's latitude is known, and altitude is known because it is 0. So formula becomes simple. Cosine A becomes simply, this is 0, sorry, minus sine delta, this is 0 because sine A is 0, cosine A is 1 because A is 0, cosine. So this is our formula for the azimuth of the rising. So simple. If you have to know the declination, you have to know your latitude where you are observing from. Immediately you get that what is the azimuth. So therefore, in case of, for example, if you want to consider sunrise, so you have the table, which I have already shown here. The table gives you the declination of sun for every day throughout the year. So this what we have found out, that cosine of A is equal to, what was just now we derived? Cosine of delta by cosine of sine phi. Sorry. Sine delta by cosine phi. Sine delta by cosine phi. So for example, what will be the A for sunrise on the winter solstice, summer solstice day at Srinagar? What is the latitude of Srinagar? So phi Srinagar is how much? Find out from, let me tell you, latitude of Srinagar will be it is 34.5 0.1 degree north. That is 5. What is the declination of sun on summer solstice day? Is 23.5. That is known because it is at the highest position in the ecliptic. So what will be cosine A? That is where the sun will rise. So it will be sine of 23.5 degree by cosine of 34.1. That is equal to, I will give you, sine of 23.5 degree is 0.399, and cosine of 34.1 degree is 0.828. This is equal to 0.482. So A will be equal to cosine inverse 0.482. That is 61.18. It means what? That if this is your horizon circle and this is your north point, you observer, you measure azimuth in this direction, is 61 degrees. So how much towards north you will see? It will be 90 degree minus 61 point. That will be the north of exact east, you will see this. And of course, it will set here. It will come and setting point will be always symmetric. Now, say interestingly, if I ask you, what will be the azimuth of sunrise on summer solstice day at pi is equal to 66.5. What will be this? It will be interesting. What is this latitude? This latitude is the latitude of the Arctic Circle. So let us see where sun will rise. So cosine A will be sine of 23.5 degree by sine of 0.5 degrees. Now you know that sine theta is equal to cosine 90 degree minus theta and vice versa. So can you not write it as cosine 90 degree minus 23.5? So this is equal to cosine 66.5 by cosine 66.5. That is equal to 1. So what will be A? 0. That means sun will rise exactly here. It will never set and it will again go there. So that is on the summer solstice day and the Arctic Circle, sun will never set. It will rise exactly at the north point and again set also at the north point in limiting. Same way, if you consider the winter solstice day, that means what will be the declination of the sun? Minus 23. So on winter solstice day, cosine A will be sine of minus 23.5 because the declination is negative. So this is equal to what? Sine minus 23.5 degree. Kaustav, can you tell me? What will be that? You find out, its answer should be interesting. What point sun will rise on winter solstice day at the Arctic Circle? You will find it should be, azimuth should be 180 degrees. It will rise, not rise at all, as a matter of fact. Just at the south point, it will rise and again set there. Anyhow, so therefore, you can see that in any day, rising and setting, they are symmetrically placed. So this is the suppose summer solstice, winter solstice. It will rise here and set here, and winter solstice it will rise here. So so therefore this is always symmetry, always symmetry. So therefore on the summer solstice day, here again it will be zero, that means it will not rise at all in the Antarctic Circle. So this you can find out, and so this is how an astronomer knows where a particular star, suppose he wants to see it at rising. There are many reasons for that, heliacal rising, etc. Where exactly Venus will rise, etc. Evening or morning. So to do that, you have to focus your telescope, and for that, approximately, you have to know what is the location where you have to focus. That means the azimuth angle, which you have to use to focus at that particular point on the horizon. So this is the rising and setting. This is also explained in the PowerPoint. Same thing, that this is the latitude circle, the object. So this is the rising point. It comes for throughout the day, the setting point. So this particular journey is the night, and this particular journey is the day. Now there is another thing which I will not discuss now. This is the heliacal rising of a star or a constellation. Heliacal rising means in the early morning, these objects are seen the last before they get obliterated because of daylight. So they are just behind them, sun is following. The sun is below the horizon, and the object is above the horizon, like this. So therefore, still you can see stars and other things because sunlight is still not bright enough. So this, and then it vanishes. This kind of rising is called heliacal rising. And it is important because in archaeoastronomy, we use this heliacal rising described in many ancient Indian scriptures and Rig Veda, etc. So there we can use it for uh, uh, dating of that particular observation. So I think what I think that it will be enough. Going into further detail will not be required for the participants of this, but some details are there, and you can always find out from standard references. So if there is any question, we can discuss it, and if any problem, I can clarify it. Now, I think I mentioned that the next topic we will start will be ancient Indian astronomy, pre-Siddhantic and Siddhantic. That we will start from the pre-Vedic era, go to the Vedic era, Puranic era, and so on, and then also medieval period up to. But all we will not go. We will not touch the telescopic period, definitely. So primarily, it will be on the pre-Siddhantic astronomy and Siddhantic astronomy. Detailed discussion about Aryabhatta's work, etc. So that will be after the examination, as Professor Mandal said, from 9th of September we will start. Is there any question or anything to be clarified? I know that many students are primarily from arts background, but I think that mathematics was not too complicated. But even if there is some doubt, I hope you can always get some help. If you think that these kinds of topics are interesting for you, this is something, we observe every day certain things, but we don't know how to quantify. Every day you observe sunrise, sunset, moonrise, moonset, but how their movements are to be quantified. I think that as a general educated person, everybody should have some rough basic idea. That's what we try to do. Like where the sun will rise, where the sun will set, or moon will rise. Everything you can find out just by the simple form. And in the case of sun, you can easily find out in Calcutta tomorrow morning at what azimuth sun is going to rise. You have the declination of the sun whole table. Tomorrow is going to be 24th of August. You know the declination of the sun. You know Calcutta's latitude 22 point some 7 minutes. I don't even. But it is slightly more than 22 degrees. And find out it. I think it will be a good exercise for Subroto and others. And check whether your calculation is correct. Then your sun exactly rises at the point which you predicted.